All right. Thank you, Catalina, for the introduction. And hello, everyone. I'm Vishal, and I work at Entropica Labs, where I spend my time between developing software tools and doing a little bit of research using QAOA. And today I'm here to talk to you about qubit routing, but specifically for QAOA circuits. But before I begin, I want to congratulate the people at Xanadu for organizing yet another wonderful iteration of QHack hackathons, and I'm happy to be here. All right, so let's begin. So before I start talking about qubit routing, let's address the question of circuit compilation first. So some of you may have heard the term before in context of quantum computation, but compilation is actually quite a popular concept in general, even for classical computations, right? So you may have heard the terminology compilers for classical programming languages, and they solve the purpose of translating your um, uh, high level language code that you define that you write to define your programs, and convert them into machine level code that your computers, your laptops are actually able to parse, right? And so compilation for quantum computers is somewhat lies in the same domain as well. So when we talk about circuit compilation, what we're actually talking about is the process of adapting the quantum circuit that you've defined for, let's say, some algorithm that you want to run on your quantum computer down to the hardware level. And that actually usually involves mapping down the circuit specific to the hardware that you're actually using to run the circuit, right? So since we have access to different quantum computing hardware these days, this compilation process will be specific to the backend that you're using. So it's going to look slightly different between, let's say, ion trapped quantum computers, between superconducting quantum computers, and so on. So this actually, the circuit compilation is something that lies between the gap which you have when you define your quantum circuit for an algorithm at the logical level, and when you finally take that circuit and you run it on an actual quantum computer. So there's a gap between these two things, and that's exactly where the concept of circuit compilation fits. So normally circuit compilation is actually an entire process that consists of a few different components. And they can actually also be understood in terms of these several compiler passes. And broadly speaking, actually, you can divide them into two different categories, right? So one of those components, one of those categories can be called a constraint satisfaction or constraint solution component, which essentially take the circuit that you have and they either decompose certain elements of that circuit into the ones that are defined or that are acceptable by the quantum computer, or try to solve some of the constraints from your algorithm. The other component is actually the optimization part of your circuit. So we all know that the present generation quantum computers are actually quite error prone, right? So when we run some algorithm on the quantum computer, we need to be sure that we can actually run the same problem in the minimum number of operations that it takes. So for example, if your circuit can run the same way by reducing the number of 2-qubit gates, we would want to do that so that we can minimize the error that we have in our computations, right? So that forms the optimization part of the circuit, of the compilation. So coming back to the first part, the constraint solving problem is about, for example, taking some high level gates in your circuit. For example, if I talk about the C phase gate, you may need to break that down in terms of single qubit rotation gates and a bunch of CNOT gates, for example. So that is usually known as basis gate decomposition and so on. And if you have, for example, a 2-qubit gate that's acting on qubits that are not actually physically connected on the quantum computer, you may need to do something that is known as qubit routing in order to map that logical level quantum circuit down to the hardware level. And that is actually precisely what we want to talk about today. So you can see that I've grayed out the other parts. So the rest of the talk will actually focus on one of these components, which is qubit routing. And even within that, we're actually going to focus only on one type of algorithm, which is the QAOA algorithm. All right, with that, before we start talking about qubit routing, I want to quickly just say a few words about QAOA. So QAOA, quantum approximate optimization algorithm, as some of you may know, is actually one of the most popular and I would say one of the most hardware-friendly algorithms, or easy for hardware to run these algorithms in today's time. Um, since in the interest of time, I'm not going to go into details of QAOA, but all you need to know in order to understand the rest of the talk is that it's essentially a variational algorithm that, like other variational algorithm, consists of an entangling layer, as you can see from the picture, and a bunch of single qubit RX gates, right? So the entangling layer is usually parameterized by this parameter of optimization gamma, and the rotation layer is parameterized by beta, right? And of course, gamma and beta in the language are called the parameters of optimization. So what you see on the screen is actually a standard QAOA circuit with depth p, where if you repeat these layers p times, you get the depth of the circuit. And the reason we're trying to focus on QAOA is because, generally speaking, the problem of qubit routing can be quite complex. And I believe looking at a simple algorithm like QAOA solves as a nice first step in the direction of understanding the entire problem in itself. And the second reason we want to look at QAOA is because there have been some studies in the literature that show that if you try to solve the qubit routing problem, for specific cases, over having like general compilers that work with any kind of circuit, there may be some areas where you can improve the performance and for example, even have some sort of scaling for the routing solutions that you have for different kind of quantum computer architectures that you have. So I've put in a link for a paper like that. You can find it on arXiv. But for now, I think we can proceed ahead. All right, so in order to understand how we encounter the problem of qubit routing or how it comes naturally, let's try to use OpenQuery to solve a problem, right? So I'm going to use a pictorial representation or like a pictorial way of trying to explain the problem. So what I do for that is imagine that you want to solve a binary optimization problem using QAOA on a device whose topology looks like what you see in these black lines and circles, right? So the black circles that you see are qubits, and the lines you see are actual physical connections for those qubits, right? But as you can see, if we map the problem defined in blue onto this physical hardware, onto the QPU, we can see that some of these gates or some of these 2-qubit gates can actually be implemented already on this hardware, but some of them are actually not connected, right? So if I want to implement this diagonal gate, I can see that there is no physical connection between Q1 and Q4 that is going to allow me to do that, right? So this is one kind of a hardware constraint that we aim to solve with qubit routing. So if I try to draw the QAOA circuit for a problem like this, you can see that it would roughly look like this, right? So you have a bunch of 2-qubit gates, you have a bunch of single qubit gates, and you want to run this on the QPU. But as soon as you try to take this circuit and run it on the hardware, you're going to realize that you face an issue, right? You cannot actually run this particular gate on this hardware, and so you need to come up with a solution to this problem. And that's exactly where qubit routing comes in, right? So we're going to use qubit routing as a solution to solve device coupling constraints, right? So we have some constraints, coupling constraints for topology of the device, which doesn't allow us to implement some of the 2-qubit gates on our circuit. So we're going to use qubit routing as a solution to circumvent that problem. So how do we do that? So take a look at this situation. So it's the same problem again, the same device, but this time what we do is we replace the position of qubit 2 and qubit 4. So we swap them. And what it does is that you now have qubit 4, or the wave function of qubit 4, in place of qubit 2. So now what you can do is originally the gate that you couldn't implement between Q1 and Q4, you can actually go on and implement that now, because now there's a physical connection between Q and Q4 after swapping the two qubits. So in terms of the circuit language, what it's going to look like is somewhat like this. So you have exactly the same kind of circuit that you did before, but in some cases, you're going to introduce these new operations, also called swap operations, that basically just replace or exchange the two qubits that you're acting on, right? Now, of course, there's a caveat with that, right? Because as soon as you exchange the positions of the qubits, for example, Q2, Q4, and then Q4, Q5, it's going to change the order of the qubits, right? So in the end, after these application of the swaps, your qubit order is going to be different now, right? So you started with this order first, and you're going to end up with, for example, a different order. And this is going to be crucial because you would need to know this order for the upcoming gates that you're going to apply in your circuit or the measurements that you're going to do in the end, right? So keeping these in mind, we're going to proceed forward. And another thing that I want you to focus on is that swap is actually an expensive resource, right? So we've heard this in the previous talks as well, but swap gate is something that you want to use judiciously. So what can we do here? So we've seen that qubit routing is actually a solution that helps us map the logical quantum circuit onto the physical hardware to solve the constraints. But not only that, in order to minimize the swap gates, we also need to solve the optimization problem so that we can come up with some sort of a mapping that uses the least amount of swaps, right? So for that purpose, we're going to define these three components. So one is the qubit selection. So depending on what qubits you choose on the physical hardware to run your quantum algorithm, the quality of your swap network will be determined. So in some cases, you may have extra swaps. In some cases, you may have less swaps. And of course, you want to choose a mapping that helps you minimize those swap gates, right? The other process is the process of routing. So you solve the coupling constraint, and then you do swap optimization to translate your circuit. And then the final thing is obviously the post-qubit sequence, right? So remember I said in the beginning, when you apply swap gates, the position of the qubit changes, right? So you need a mechanism where you can track what the final order or the final sequence of those qubit looks like after the shuffling. Okay, so now we're going to talk about, in the last few minutes, we're going to talk about how we can implement this function, right? So if we need to design our own qubit routing algorithm, we need to keep these three components that we discussed previously in mind, right? That should be the output of our solution. But what do we need as input to implement that solution? And that's simply just going to be the device coupling map, which is going to define the constraints that you have, and then the circuit that you aim to route. And then very simply, your function is just going to be as simple as something that takes an input as the coupling map of the device or and the circuit that you want to route. And then in the end, what you get as output is the qubit mapping, the routed circuit, and then the post-swap qubit sequence. All right, so there are several ways that you can implement this, but today I'm actually going to focus on how you can do this within OpenQAOA. So OpenQAOA is this a library that we developed at Entropica Labs for solving for using QAOA to solve different kinds of problems, right? So within OpenQAOA, it's actually quite simple to come up with your own solutions to implement swapping. And all you require is actually defining a simple function, a Python function, that takes as input the device and the circuit that you want to route, and implements that algorithm and gives output as the things that we just talked previously. So of course, when you develop this function, you also need a way to test this test how your function is doing, how it's progressing, and so on. So doing that is actually quite simple in OpenQAOA. So you're going to start with a bunch of import statements, right? So you're going to import a bunch of stuff from OpenQAOA. You're going to define your problem. So in this case, it could be a max cut problem. You're going to create your device. In this case, I just used some QPU from IBM. And then I'm going to solve my QAOA by first setting the device that I've created, and then compiling the problem by passing the max cut and my routing function, right? So you can see that the routing function here is sort of like this dependency injection that you put in your model, and then you basically optimize. Now, of course, since this is an expensive step, you don't want to do it on a QPU, right? So you may want to test your function initially on, for example, a simulator that kind of emulates as a QPU, right? So in that case, you can just simply add this extra field in your device, and then it's going to be the same process. And instead of running on a QPU, it's actually going to run on a simulator. So hopefully I was able to give you some basic background in the field of qubit routing. And I think I hope OpenQAOA serves as a good testing bed for you to test your own qubit routing solutions and algorithms. And of course, we're going to release some documentation that's going to help you with the tasks and so on. But for today, I thank you for your attention, and I'm going to take up some questions now. Thank you.
Thank you so much, Vishal. It was really cool. I really like your presentation, especially when you have memes and GIFs. That always brings a smile, right? um, it takes a little bit of the technical part away, and it makes you kind of realize that this is fun. I mean, you do know it. If you do this, you do know it, but it's a cool environment,
exactly,
right?
Yeah. Yeah.
I was curious about like how you got this idea. I know that qubit routing is very important, right? But you explained some, like, not all qubits are connected to all qubits, and so by adding these swap gates, then you can get like stuff that you can actually implement on hardware.
Yeah.
Like, does this idea come from a paper, or did it come from the realization like we're having trouble implementing stuff on hardware?
So actually, the idea I think comes a little bit from both areas. So I've been working with QAOA and different kind of algorithms, variation algorithms for the past 3 years. And in most cases, what I've seen is that this part of compilation is something that most of the hardware companies keep for themselves, right? So they allow you a lot of freedom in the kind of gates that you can define, or the way you can define the circuit and submit your problems for execution. But when it comes to compilation, it's mostly just handled by hardware companies, right? Because naturally, obviously, because it's also a challenging step, right? But from our experience within the company running different problems, what we've seen is that sometimes when you try to run it over like bigger problems, for example, like over 40, 50 qubits, what we see is that the de facto solutions for qubit routing may not do as well if you try to design your own qubit routing solutions, right? And one of the hypotheses we have for that is that these qubit routing solutions are generally designed for any kind of quantum circuit, right? So they lack that specificity. So, like I said in the talk as well, if you're trying to solve for a QAOA type problem, so QAOA is a really specific kind of uh, 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 algorithm, right? Where the gates that you have, they hold this special commutativity rule, right? So you can just swap the gates around, and you don't really have to care about the order because they all commute with each other. So with this really nice property, I believe that you can create these specific solutions for routing that can, in some cases, end up outperforming some of the de facto solutions that you have for routing out there. And I believe like this is not something that we only think. The link to the paper that I've mentioned in the talk, they also go on and present this idea, and they show that if you try to implement qubit routing for specific problems, there may be some areas to improve and some improvisations that you can do, which will benefit over generic solutions, for example.
Okay. Thank you. Thank you for that answer. We have a couple of questions from the chat. Broken Symmetries is asking, are there any devices with better coupling maps than others so that we need less routing?
So that's actually a really interesting question. And I hope we had like devices with fully connected couplings, which we do in some cases. So we have them for ion trap computers, but without going into the details, they can actually, through physical processes, they can actually implement and all-to-all connectivity, right? So you can actually have qubits on ion trap devices which have full connectivity. In that case, you don't really have the problem of qubit routing, right? Because you can implement all of the 2-qubit gates that you want. But as far as I know, for a lot of other hardware technologies like superconducting qubits and so on, they are kind of like etched onto the wafers, right? So they are like physical connections on the qubits, and there isn't much you can do about it. So the qubits that are connected are the only ones that are connected, and you can't change anything about that. All you can do is implement swap gates over there. So so just to summarize, in some hardwares you can have better connectivity, that is fully connected qubits. In other hardwares, depending on the architecture that is used, you can have maybe connectivity with maybe 3 or 4 neighboring qubits.
That's right. Thank you so much, Vishal. So we're out of time for questions, but everybody can still ask your questions on Discord. So thank you so much, Vishal.
Right.
And thank you, everybody,
Thank you
for
so
asking
much.
questions.